Hi to everyone, I'm Nicola Solini and I come from University of Verona. And in this talk I will talk about static analysis for high-level quantum program languages with a focus on dealing temporary variables. So working with quantum computing is something great. I think that we all agree. But when we put together the program languages with quantum computing, we introduce some new challenges due to the feature of quantum computation. We say that in general, we can say that these challenges are related to the no-cloning theorem and the implicit measurement principle with the entanglement. The first one implies that we cannot copy a variable in general. And the second one forces us to pay attention when we want to discard a variable. In fact, if we don't do it in the proper way, we cause some implicit measurement that can lead to side effects due to the entanglement. So the POP solution to these two problems are using linear types. In fact, if we use a linear types, we need to use a variable exactly once. So basically, we use variable at most once, so we cannot introduce copy, implicit copy, and we must use all variable. This means that when we discard a variable, we must do it explicitly. So since we explicitly discard variable, we basically are sure that every time we discard a variable, we say to the compiler, make the computation of this variable, of these resources. And in particular, in this talk, we focus on this feature of this solution, so the discarding of variable. With the linear types, when we have a program like this one that uses some local variable, so in this case we have the variable a that is defined inside a function and then it's not returned, you can see that we will define this variable multiple times, but the last time, at line 5, we define the variable a, but we don't return it. This means that this program introduces an implicit discarding of this variable. So in fact, if we treat the type qubit linearly, the type checker will return an error like this. And if we want to make this program well typed, we need to explicitly discard the variable. So we will add a function, a discard function, depending which program we are using, which language we are using. So in this case, we have used all variable, also the last definition of a it used. And in this version of the program, we are sure that this variable will be properly handled by the compiler since we have discarded it. You see that when we use linear types, the duty of insert discarding in the language, in the program, is left to the programmer. In fact, the programmer must explicitly discard all the variable or temporary variable in a program. And this can make the use of the quantum program languages harder because it's something that the programmer must care about. So we want to define a more easy approach to this problem. And in particular, we define a static analysis that collects all the information about variable used, and then we can use this information to take a program that uses variable at most once, so a program that respects a more weak constraint, respect to the constraint of linear types, and then we can transform it in a program that is variable exactly once. How we do that? We do that adding the discard function where it is needed. So in this case, returning to previous example, with our approach, instead of returning an error like this, we do not return an error. Instead, we analyze the program, and we automatically add the discard function. Okay, we can see our approach on a more complex example. This is a program in which there are 3 implicit discarding. In particular, there is the variable r, that is a parameter of the function, and it is used only in the if branch, so when the computation goes to the other branch, we do not use this variable, and when we arrive to the return, there is an implicit discarding. Similarly, there is the same with z, that is used only in this branch and not in the other branch. And finally, there is the variable c, that is redefined at line 9, but is not used. So a type checker will return an error on these 3 variables. Instead, with our approach, we analyze this program. In particular, first we build the control flow graph, then we perform the analysis, And finally, we use information from the analysis to insert the discard. So first, we build a control flow graph. We see that we represent the program with a graph. A control flow graph is basically a graph in which each node corresponds to a program point. The edge indicates the flow of the computation that go from a program point to the other. And on the edge, we put the label that correspond to the statement that are executed when we go from a point to another. You see that we add two special labels. In particular, this label indicates which variable are passed are parameters. And these two labels are used to indicate which is the true branch and the false branch when there is a branch. And we ignore the classical variable since the discard only it is need only with quantum variable, so we can just ignore the classical part of a program. So after we have defined the control flow graph, we need to perform an analysis. In particular, our analysis starts from classical live analysis. So we first recall the concept of liveness. When we have a program that could be modeled by a control flow graph, we say that a variable x, it is live in the node u if it has been defined before in the program, and it will be used. So in this case, the variable x is live from this node, I mean just after the edge, until this node. So in this part. And in particular, we define two types of liveness because we need a more accurate information. We define the safe liveness, so we say that a variable is safe live in a node if it will be used in all paths from that node. So in this case, the variable exit used in both paths, so it is safe live in U. And we define another type that is unsafe liveness, that is when a variable is used only in one path. I mean, it's not used in all paths. So in this case, it is used only in one path and not in the other, so the variable is unsafe live here. Of course, this variable is safe live in this path because there is no branching. So so to compute our analysis, we need to determine for each node which variable are safe live and which variable are unsafe live. To do that, we define a pair of sets, the set S that refer to safe live variable, the set U that refer to unsafe live variable, and we compute this pair of set for each node of the control flow graph. So as the liveness analysis, our analysis backward, so we need to start from the exit node and go backward in the sense of computation. So we start from the exit node. We initialize the pair of set to empty, since there is no live variable at the end of the program. And then we compute all the other pair in the other node. So first, in node 6, we add the U to S because return U use the variable U. Similarly, in node 5, we add the variable C because here we are using variable C. In node 3, we remove C because C is defined, so it's no more live, so it's no more safe. And we add variable R because it's used by HR, Adam R. Similarly, we do the same in node 4. And then we arrive to node 2 where there is a join. And in particular, here is when the other set is used. In fact, you see that the variable U is safe in node 4 and in node 3. So it's used in both paths. So in this case, we can put the variable U in S also in node 2, because since it is safe in both nodes, it will be safe also in the join. Instead, you see that the variable R, it is safe only in node 3, but not in node 4. This means that it's used only in this path. So we move R from S to U, and we do the same with Z, because it's not safe here. So basically, when we have a join, we make an intersection between the two S nodes, a union between the U, because in this case are void, and then the part of S that are outside the intersection, we move the variable, the extra variable, we can say, from S to U. And then we can go on the analysis. In node 1, we remove U because it's defined, and we do the same in the start node. Now that we have all the information about the variable use, we need to add the discard. In particular, we need to discard two types of variables. The variables that are never used, so the variables that are never live, and the variables that are partially used. so the variables that are in U. We start with the first case. To find a variable that is not live, so not used, we need to check all the definition in the code and look if the variable that has just been defined, it is live just after the definition. In this case, you see that here we define Z and R, and they are live, so it's okay. U is live after the definition, so it will be used. The same with the first and second definition of C, but the last definition of C defines C, but C is not live just after the definition. This means that this C is not will be used. And in this case, we can add the discard just after the definition. Then there is the other case that is more complicated, when a variable is in U. In particular, in this case, there are R and Z that are in some U. We start from R. When a variable is in U, this means that there is some path that do not use that. And this is the reason for which, the reason that caused that the variable end in the U. So we need to find that not using path, basically. How we do that? We look for each node U, the successor of that node. You see that, for example, node 1, the variable is in U, but it is live in the successor, so it's okay. Instead, in node 2, the variable R is in U, and if you look to the successor, in one successor, the variable R, it is live. So this means that this path will use R, so we cannot insert the discard. But there is another path that do not use R. In fact, in this node, the variable is not alive. So this means that the path that cause the unsafeness, so the path that do not use R, is this path. So in this case, we add the discard at the beginning of that path. And then we do the same with Z. In fact, it's unsafe here and unsafe here. After node 1, it always used. After node 2, it used only in node 4, so we discard in the other path. So we are starting from this code, and without that require some discard function, because there are some implicit discarding, and without recurring to program, without programmer intervention, we add all the discards that are needed. So basically, with our approach, we can relax the type system of a quantum program language, so in general, a language that need linear types, and automatically handle the part of discarding variable, so we can make the use of quantum languages, so in general language, more easier, since the constraints that are required, the constraints that the programmer must follow are more easier. And we can conclude. In conclusion, we implemented this analysis for Guppy language, a new language that Quantinuum are developing. And in fact, all the examples that you have seen before are a fragment of a simplified version of Guppy code. And we test also this analysis in some simple code. And as a future work, we aim to give to integrate this analysis in the Guppy compiler, maybe with the help of Quantinuum if they want. And moreover, we think that we can improve this analysis. In fact, it's not always the computation, so we can say a safe discard is not always needed. For example, if a quantum variable is always a classical value, or it is not entangled with other variables, we can simply drop it without an intervention. So we think that we want to improve our pipeline by adding other analysis, for example, entanglement analysis, to understand the group of entangled variable, and also other classical analysis like constant propagation or an interval analysis, maybe to understand to better model the control flow. So, for example, if there is a for loop, and we can understand that the for loop will be always be executed, we can then do a better representation of the control flow, so gain a more precision with our analysis. And yeah, that's all.
Thanks, Nicola. We have time for a few questions. Jens? You mentioned entanglement here right at the end.
Yes.
Is it actually safe to discard a variable that's entangled with another variable?
I mean, it's not safe to discard a variable that's entangled with other variable. It's safe to discard a variable that is not entangled with other variable, because the fact of discarding is that if I discard a variable, it means that I cause an immeasurement, so I can cause some side effect. But if I measure some variable that is not entangled with other variable, it will be not.
Does your analysis handle?
No, now my analysis does not handle the entanglement part. We just find for temporary variable, basically. So we find that for variable that are like in this example, we discard all the variable that are not that in the computation are not used from a point. So for example, in this case, the variable R and Z are not fully used, so we discard them. But we can improve this pipeline adding an entanglement analysis. So for example, if R it is not entangled with other variable, this discard is
but isn't it true that you may, in this example here, if the variables are entangled, you may be discarding too early in your example here? An entanglement would mean that you should wait and discard later.
I mean, okay, it's depend. It's depend of not. It's depend in this case. No, I mean, not always. I mean, there are some cases in which we cannot uncompute a variable due to entanglement, but I mean, this is not the problem, because in theory, we simply say discard. Like, I mean, in Guppy, you write a program like this. The fact that this variable is uncomputing now or uncomputing after is something that will handle the Guppy compiler. We are just saying discard. But in the entanglement analysis is something that work more with the compiler. So we can say this variable is used. I mean, make this uncomputation is useless because there is no side effect, for example. Or make this uncomputation is danger. So you have to wait. Yeah.
Thank you for the talk, first of all. Also, maybe to add a comment to your question, I mean, there's this automation called Uncom. We already discussed this earlier. And within Uncom, this disentangling would be possible. I think in this particular case, it would not be possible because your particular program has a feature that is, it's not queue-free. In Uncom, there's this property called queue-free, and it's caused by the H gate on the Z, and then C.
Okay. Yes. In this case, the variable C. Okay, yes, not queue-free. Yes.
Yes. So I mean, it would probably still be possible to disentangle it by reversing the last C0 gate, like flipping the inputs. That would probably disentangle it, but it would not be possible to perform this in an automated manner. You need to know as a programmer that it is this kind of structure. But yeah, I mean, this was actually my question: is there also some kind of disentangling automation behind it? So I think you already answered it.
Yeah. Okay. Yes, because we are considered the different side of the problem. So we are just saying discard. What the discard do is something that is related of the program that we are analyzing. So for example, this is Guppy. I mean, you just add the type of the function, and this is a Guppy code. And in Guppy, you just say discard. So I mean, the Guppy compiler that I think that actually does not completely exist yet, will, in theory, we should handle the fact, like in this case, or maybe, I don't know, it will be do something about the not possibility of computing, for example, or the not free fact.
All right, let's thank Nicola.